get started. We talk about orbitals, and we did mention orbitals in terms of the quantum numbers yesterday in lab. What is an orbital? What does the Schrodinger wave equation, how does it define orbitals? Essentially, it's the region in space, the area in space where we expect an electron to be most of the time. And the way that works is, the way that electrons and all quantum particles work, they have very interesting properties. And one of the properties of quantum particles is that they truly have no set location. The Heisenberg uncertainty principle talks a little bit about how if you know the exact position of a particle, you can know nothing about how fast it's going. And if you know exactly how fast it's going, you can know nothing about the exact position. When we talk about orbitals, we're talking about sort of the region in space. Sometimes we think of electron clouds, right? So this region in space, this cloud where the electron is going to be 90% of the time, right? And that's how we sort of pick up on these shapes. That's how we draw these shapes of these orbitals. And so, if this is our nucleus in black here, and all the possible points for an electron to be are in green, when we talk about the distance away from the nucleus for that particular electron, we're going to talk about it in terms of the 90% probability. And so that's what this black ring represents here. 90% of the time, the electron is inside that sphere. Remember, this is in 3 dimensions. And 10% of the time, it's outside that sphere. And so if we were to look here, that distance from there to there is, say, the same as from here to here. So that's 0 for distance from the nucleus to there. And if we're calculus people, we would say that the area under the curve is the probability. And so that area, that's 90% of the area under the curve. And then that 10% is the farther away from the nucleus. When we look at higher order orbitals, so this would be the 1s orbital here that I'm tracing now. We would move up to the 2s, to the 3s, and then the 4s. Right? And the electron moves a lot more when it's in the n equals 4 energy level. And so that probability, that 90% probability, has to be larger for the 4s electron than it does for the 1s electron, because that electron's moving a lot more. Okay. And so where do these, how do we look at these in terms of shapes? For atomic orbitals, again, we're going to start at the s orbitals. Remember, those are when L equals 0. We have s orbitals. Here we see the different sizes, right? Again, remember, the nucleus is in the middle of these spheres. And so from 1s to 2s to 3s, we see that they get bigger, again, to accommodate 90% of that probability. When L equals 1, we get p orbitals. And the shape of the p orbital kind of looks like a figure 8. A lot of textbooks call them barbell shaped. These don't really look like barbells to me, but that's a shape that's how a lot of textbooks describe that shape. And you'll notice that these are all 2p orbitals, but they're oriented along different axes. And we'll talk about that in just a minute, but that's the general shape of the p orbitals. Moving up to d orbitals, they get funny looking. And these are all the 3d orbitals. We talked yesterday in lab that n equals 3 was the first time we had some d orbital possibilities. And there's 5 different d orbitals. Remember, we know that because there's 5 different values of m sub L. And these are what the different orientations of those d orbitals are. Now, you do not need to memorize these. These are a lot more complicated than the p orbitals. And we'll talk more about p orbitals in just a minute. But going through and using our knowledge of quantum numbers, for orbitals in the 4D subshell, what are the values of n, l, and m sub l? So for 4D subshell, what are the possible values of n?
5?
Again?
Would it be 5?
No. What does this 4 tell us? So remember that 4 is the value for n. Whenever we are giving you a subshell, we tell you what the shell is first, n equals 4, and then we tell you the subshell with a letter. And so for the 4D subshell, n has got to equal 4. If we're in the D's, what does L equal?
3, 2, or 1, or 0.
So it tells us that, so 3, 2, 1, or 0 are the options for L if n is equal to 4. Because it tells us that we're in the 4D subshell, which value of L corresponds to D?
2.
2, absolutely. And so we got to try to move away from sort of thinking about all of these have multiple values and start honing in on if I'm talking about a particular orbital or a particular subshell, there's only certain values that are allowed. Now, because it only gives us information about the subshell and not about the orbital, what values of m sub l are possible?
That would be -2, -1, 0, 1, 2.
That's it, right? And so the as specific as we've gotten is to the subshell. So remember, this is shell, subshell, orbital. And remember, m sub s gets us all the way down to which electron we're talking about, right? So we need 2 quantum numbers to define subshell, n and l. We need 3 quantum numbers to define a single orbital, n, l, and m sub l. We need all 4 quantum numbers to define a single electron within an orbital. Okay. All right, very good. So I told you we'd talk a little more about those p orbitals, but we determine the orientation in space based on the value of m sub l. We talked about how L is the angular momentum quantum number, and m sub l we called the magnetic quantum number. It tells us the direction of that magnetic field based on those electrons whizzing around. So the electrons moving through space rather than the electrons spinning, right? So think about the Earth orbiting the sun rather than the Earth spinning on its axis, right? Each of those generates some magnetic field, even though for the Earth it's super tiny because it's not moving around the sun very fast, right? And so for m sub l, we have 3 possible values, -1, 0, +1. So we have 3 different p orbitals. Each of those p orbitals takes on a different orientation in space, right? It doesn't really matter which m sub l value you assign to x, y, or z, you know, that there's no real difference in those. But generally speaking, we would say that, you know, for the p orbital that's oriented along the x-axis, we would say that this has an m sub l of -1. For the one oriented along the y-axis, we'd say that this is an m sub l of 0. And for the one oriented along the z-axis, we'd say that this is an m sub l of +1. Right? Now, in the previous example, we talked about how there are 5 possible values of m sub l when L is equal to 2. So for the D subshell, again, we've got those 5 possible values for m sub l, and we end up with 5 different orientations in space. Again, I'm not going to go through and try to figure out, you know, what we call these, how we refer to these. They get even crazier when we talk about F subshells or G subshells. But for now, we're just going to know that each value of m sub L corresponds to a different orientation of that orbital in space. So still working a little bit with quantum numbers. The total number of orbitals associated with the principal quantum number of 3. Okay? So all we know is that n equals 3. What are our possible values for L?
Zero, 1, or 2.
That's it. L equals 0, L equals 1, L equals 2. If L equals 0, what are our values of m sub L?
0.
0. If L equals 1, what are our values for m sub L?
Negative 1, 0, or 1.
That's it. And for 2?
-2, -1, 0, 1, 2.
That's it. Okay. And so again, N corresponds to shell, L corresponds to subshell, and m sub L tells us something about orbitals. And so for all these n equals 3, how many orbitals do we come up with?
9.
That's it, 9 orbitals. Let's do n equals 2 real quick, and we can make some connection here. If n equals 2, well, L equals 0 and L equals 1. M sub L equals 0, M sub L equals -1, 0, or 1. How many orbitals do we have when n equals 2?
4.
So what's that relationship?
The number of orbitals is n squared.
That's right. So n squared equals the number of orbitals. Okay. All right. So, we talked a little bit in lab yesterday that when we discuss quantum numbers, we have this Pauli exclusion principle, and so just to reiterate that Pauli exclusion principle. No 2 electrons in an atom can have the same 4 quantum numbers. Remember, we equated this a little bit to seats in an arena, right? N might tell you which bowl you're in. Are you close to the field, or are you far up in the nosebleed seats? Then L might be your section number, right? So you're in section 104. M sub L give you your row, so you're in row G, and then M sub S give you your seat. So you're in seat plus a half, right? And so, because we don't want to, share a seat with somebody, similarly, those electrons don't want to share an energy, share a location in space with another electron. And so this Pauli exclusion principle tells us that no 2 electrons can have the same 4 quantum numbers. I'll also use this little space here to just try to reiterate again that in order to know something about the shell, all we need to know is N. Okay? If I need to know something about a subshell, yeah, I need to know L, but I need to know N too. So I need to know N and L. If I need to know something about a particular orbital, I need to know N, L, and M sub L. And then if I'm going to talk about a particular electron, I need to know all 4 quantum numbers. N, L, M sub L, and M sub S. Right? If you want to know your seat, you can't just say you're in row G, seat 2. because there's lots of rho g's in every section and every bowl of that arena. You need to know all of those details. All right, so how do we use this information? How do we use this sort of arrangement of atomic orbitals? We go from, we have the s orbital when n equals 1, we have the s and the p orbital when n equals 2, sp and d when n equals 3, and on and on. So what do we do with those? Well, if we have an atom that happens to have just one electron, right? Hydrogen, for example, all of those subshells have exactly the same amount of energy. Right? And so here's the n equal 1 down at the bottom, n equal 2. The 2s and the 2p subshells have exactly the same amount of energy. Notice the y-axis here is energy. For n equals 3, the s, the p's, and the d's all have exactly the same amount of energy. N equals 4, s, p, d, and f all have exactly the same amount of energy. And so this looks very similar to what we saw at the beginning of chapter 7 when we talked about that Rydberg equation and that Bohr model of the atom, where you have these discrete energy levels. And so that is still true. And this is the reason why that Rydberg equation works very well for hydrogen, because any electron at n equals 2 is going to be the same energy. And so going from n equals 2 to n equals 1 has a set amount of energy. However, if we have a multi-electron atom, anything other than hydrogen, right, which is most of it, all of a sudden, these energies are not exactly the same when n is constant. And so here's 2s and 2p. See, those are different by just a little bit. 3s and 3p are different. 3s and 3d are very different. 4s and 4p have a big jump. And then the 4d is there. And then 5s kind of sneaks in between those two, right? Notice how 4s snuck in between the 3p and the 3d. And so now that we have multiple electrons, the energy levels of those orbitals shift around. The reason being that as soon as you put an electron into an orbital, that orbital energy changes a little bit. If it's empty versus if it has an electron in it, that orbital energy shifts a little bit. And so for elements that have more than one electron, lots of these orbitals are full of electrons, and so those energies shift around. Okay. Notice there's not a nice clean equation like the Rydberg equation when we talk about the energy of these energy levels. We are not getting into that. That's for Chem 314 if you want to go that far. But for now, we just need to know that the energy is given by the Schrodinger equation. We're not going to solve the Schrodinger equation in this course. Okay. So how do we know where electrons go in a particular atom? Well, there's something called the Aufbau principle, and it's kind of common sense. But the Aufbau principle tells us that we start in the lowest energy orbital and we just work our way up, right? Nature likes things to be low energy, and so we're going to start at the lowest possible energy, and then we're going to fill up our electrons that way. And so if this is our, let's say that we had something with 10 electrons, right? We're going to fill up our electrons in order. How many electrons fit in each orbital?
2.
2, that's right. We can have one spin up and one spin down. And so in the 1s orbital, I'm going to draw each electron with a little arrow. I just put a single head on the arrow. If you want to put both heads on the arrow, that's fine. It's just faster for me to put one head on the arrow. And so there's one that has m sub s of +1/2, so it's spin up. There's one that has m sub s of -1/2, so he's spin down. There's 2 electrons. There's 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7, 8, 9, and 10. There's 10 electrons. And so that's that's how those electrons would be sort of, that's where they would be located in an element with 10 electrons. 10 electrons, that must be neon. And so neon has this electron configuration, we would say, of, well, he's got 2 in the 1s orbital, and so we write 1s, and we do a little superscript 2 just to show how many are in that orbital, in that subshell. Then the next in energy is 2s, and so there's 2 electrons there as well. So he's 2s2. The next highest subshell is 2p, and there's 6 electrons in the 2p subshell, and so that's what goes next. And so that's what we call the electron configuration for neon. We'll get more practice with that here in a minute. Okay. All right, in this example, I chose one where we completely filled up a subshell. Right? So now we're going to talk a little bit about Hund's rule. And Hund's rule tells us what to do when we don't fill up a subshell. Okay? And so what Hund's rule tells us is that when electrons are added to an orbital, to a subshell, they will spread out across the available orbitals, and their spins will be in the same direction. Okay. So if you allow me one more time to do this arena analogy, this stadium analogy, right? You'll have to imagine that all of our rows only have 2 seats, right? Because they have a spin up and a spin down. And so you can imagine that if you were in a section in a stadium and there are, 5 rows, each row has 2 seats. If there's already somebody sitting in one row, but the other row was empty, would you go and sit next to that person, or would you sit a row behind him and have the row all to yourself? Well, electrons essentially do the same thing. It's lower in energy for them to spread out than it is for them to be packed in the same orbital. It has a little bit to do with the fact that electrons are negatively charged. And if we put 2 negatively charged electrons in the same orbital, there's a little bit of negative repulsion there. And so it's a little bit higher in energy for them to be in the same orbital if they don't have to be. And so let's say that we have something with 8 electrons. I'm going to redraw our energy diagram here. And now let's say we have oxygen. Oxygen has 8 electrons. Oops. Got ahead of myself. Well, he still needs 2 electrons in the 1s. We're going to fill that up first, lowest in energy, following the Aufbau principle. Next lowest in energy is 2s. We're going to fill that up, lower in energy, following the Aufbau principle. We've got 4 more electrons. And so what Hund's rule tells us is that those electrons will go in like this. Right? They'll go into those 3 orbitals with their spins in the same direction. And then we won't start pairing up electrons until we have to, right? Let me go in real quick and draw in the 3s. 3s is the next highest orbital, next highest subshell. And so because we still have empty spots in the 2p, that last electron is not going to jump up to the 3s. He's going to stay in the 2p, but he's going to start being paired. So this is Hund's rule. So we leave electrons unpaired if possible. Okay. All right. So there is sort of a shortcut for us to remember how to fill orbitals, right? Again, this is something that maybe you saw in high school, but if we just write out, if we just write out the possible subshells, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. I'm not going to put 5g because I told you on Monday we don't actually have any electrons. There are no elements that have electrons in g orbitals, and so I'm not going to put that there for now. If we wanted to know how the order in which to fill these orbitals, we're just going to draw some diagonal lines. So we're going to do the 1s first, then the 2s. Oops, I'm drawing my arrows backwards. 1s first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, the 4p, and the 5s, the 4d, the 5p, and the 6s, the 4f, the 5d, and the 6p, 5f, and the 6d, and then the 6f. Okay. This is one way of doing it. We'll talk in just a minute about how the periodic table is your friend, and the periodic table can help you sort of figure out where you are as well. But this is sort of a nice trick to know how to fill those subshells. Okay. All right. So for quantum numbers for an electron in a 3p orbital, if we're in a 3p orbital, what does n have to be?
3.
N has to be 3. What does L have to be?
2, 1, or 0.
So if it's a p orbital,
2. Wait.
1.
yeah. So remember that each letter corresponds to a different value of L. S is L equals 0, P is L equals 1, D is L equals 2, and F is L equals 3. Right? So that's one of those things where you just have to know which letter corresponds to which value for L. Okay. Now they don't tell us which orbital it's in. It just says a 3p orbital. And so give me a possible value from Sibel. Any possible value.
0.
Excellent. And then what's a possible value from Sebes? Because it asks for all 4 quantum numbers. What can M sub S be?
Positive.
Plus a half or plus a half.
Yeah, it can be plus a half or minus a half. So those are the 4 quantum numbers for an electron in the 3p orbital. If I just drew out the 3p real quick, just the 3p, we usually go across and number them -1, 0, +1 for the M sub L values. Right? So the electron you've just described is right there. Right? So we're not going to fill the 0 level first. There has to be at least one other electron in there. That's okay. And so this is absolutely correct. There's an electron. N equals 3 because we're in the 3p, L equals 1 because we're in the p, M sub L equals 0 because we're in that middle space, and then M sub S is a half because we are spin up. Okay. Sometimes these questions ask for a particular electron in a particular atom, and we'll see another example like that later on. So electron configuration, we talked a little bit about this already. When we are writing out an electron configuration, we're going to, just like we would do if we were adding in electrons, we're going to start at the lowest energy, work our way up. And so let's do, well, we already did neon. We looked at oxygen, but we didn't actually write out the electron configuration. I'm just going to draw out the orbital diagram without the difference in energy levels, otherwise it'd take up the whole slide. But we said oxygen was full in the 1s, full in the 2s, and then had 4 electrons in the 2p and looked like this. So the electron configuration for oxygen, 1s2, 2s2, 2p4. Okay. If we're just looking at the electron configuration, there's no way for us to know that 2 of those electrons are unpaired and spread out. That's just something that we have to recognize is going to happen because we know that we're going to follow Hund's rule and the Aufbau principle. If we looked at something like aluminum, who's got a periodic table handy? How many electrons are in aluminum?
13.
13, excellent. So because each orbital has only 2 electrons, we know we're going to need at least 7 orbitals. So let's work our way up. 1s, 2s, 2p, 3s, that's 6 orbitals. Now I can't only draw one 3p orbital because there's 3 of them. So we have to draw all of them out. 13 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 electrons. And so we would write aluminum as 1s2, 2s2, 2p6, because he has all 6 electrons there, 3s2, 3p1. All right. How about titanium? How many electrons in titanium?
22.
22. And so titanium is the first element that we have talked about that has some d electrons. If you remember our little diagonal trick, we go from the 3s to the 3p and then the 4s, and then we do the 3d. So the 4s comes here, 3, 4, 5. That's the 3d subshell. And so titanium, 22 electrons, 1 up, 1 down, and 1s, 2s, 2p, we're going to follow Hund's rule, 3s, 3p, we're going to follow Hund's rule, 4s, and then 3d, there's our 22 electrons for titanium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. There are some resources that you might find that when they write out the electron configurations, they keep all the 3s together, they keep all the 4s together, even if that's not the right energetic order. It really doesn't matter to me. I just write them in the order that we put the electrons in. Right? Okay. So titanium had 22 electrons. Aluminum had 13 electrons. Oxygen had 8 electrons. Let's do one more that gets a little tricky. Let's do selenium. How many electrons in selenium? Maybe that's not so tricky.
34.
34 electrons. Now, I'm not going to draw out all those electrons in an orbital diagram. I'm just going to write the electron configuration. I know the order that they go in. I know how many there are, so I should be able to count it up. So there's 34 electrons, so it should be 1s2, 2s2, 2p6. I'm counting up as I go. That's 10 so far. 3s2, 3p6, 4s2. That takes me to 20. 3d10, there's 30. 3p6. Oops, 3p4. Sorry, 34. That's where we're going.
Don't you mean 4p, sir?
I do mean 4p. Thank you. Thank you. Yep. Okay. So we know the order that we load electrons in. We know that those superscripts tell us the number of electrons in each of those subshells. And so we don't have to draw out the orbital diagram. We can just write out the electron configuration. Okay. All right. One more thing, and then we'll change gears a little bit. We've talked a little bit in chapter 2, especially, about how the noble gases don't really react with anything. We also talked about how, in that same chapter, chapter 2, how the alkali metals all lose one electron, so that they have the same number of electrons as noble gases. All the halogens gain one electron, so they have the same number of electrons as noble gases. Noble gases have very stable electron configurations. A shortcut that we can do for ourselves is to essentially take that noble gas and replace the first part of our electron configuration with the electron configuration for the noble gas. And so for selenium, what's the next smallest noble gas before selenium?
Argon.
Argon. Argon. And so argon is 1s2, 2s2, 2p6, 3s2, 3p6, right? All of this equals argon, right? They have exactly the same electron configuration. And so one of the ways that we can write the selenium electron configuration is to just say that he's argon. We put that in brackets. And then we just say everything past argon. 4s2, 3d10, 4p4. That's a nice shortcut to use, so we don't have to draw, so we don't have to count up all that stuff. We can also look at argon and say, well, I know that argon is 18 electrons. And so I just need to add in my 16 more. So I start with 18, then 4s2, that's 18, 3d10, that's 28, or that's 20, and then 30, sorry, and then 4p4, that's another 4 for 34 electrons. Okay. All right. Now, one of the things that we discussed in lab yesterday was that if we have unpaired electrons, that's we call that paramagnetic, and that has some magnetism. If all the electrons are paired, we call that diamagnetic, and those doesn't really have much magnetism. And really, the only explanation that I gave you was that those subshells were full, right? It's not just that there's an even number of electrons, because if you look here, oxygen has an even number of electrons, and he has 2 unpaired electrons in his 2p. Titanium has an even number of electrons. He's got 2 unpaired electrons in his 3d. And so we can't just go based on the number of electrons. We actually have to know whether or not that particular subshell is full to know whether or not it's going to be paramagnetic or diamagnetic. So again, talking about paramagnetism and diamagnetism, if we have a situation where we have 2 unpaired electrons, like here on the left, That's what we call paramagnetic. Here we have some paired up electrons. They've sort of drawn them very far apart, but here all of our electrons are paired. And again, we call that diamagnetic. All right. Any questions so far?
So are they diamagnetic if all of the shells are like completely filled?
Yep, absolutely. So if all the shells are filled, then all of those electrons have to be paired up, and so they are diamagnetic. Yep. Okay. All right. Moving on then. How many electrons, maximum number of electrons that can be present if the principal quantum number is n equals 3? So the principal level when n equals 3. Well, if we think back, n equals 3, how many orbitals are there when n equals 3?
9
9. And how do we know that?
n squared.
That's it. And how many electrons can we fit in each orbital?
2.
2, 1 up and 1 down, right? So you have 18 electrons, 2 electrons per orbital. Okay. And so we can only have 18 electrons where n is equal to 3. Okay. All right. Oxygen has 8 electrons. Write the 4 quantum numbers for each of those 8 electrons in the ground state. I'm going to go ahead and draw out the orbital diagram for oxygen, even though we've done it before. 1s, 2s, 2p. We know that he looks like this. Hund's rule tells us to spread some things out, and then we're going to go back. Okay. All right. So we're going to write all 4 quantum numbers for all 8 electrons. And so, you could make a little table or however you wanted to do this. But for this first, for these 1s electrons, what's the principal quantum number?
1.
That's it. I'm going to make a little table here. N, L, M sub L, and M sub S. So for both of these, N is 1. What's L for the 1s electrons?
0.
0. What's M sub L for the 1s electrons?
0.
0. And we've got 1 that's plus a half and 1 that's minus a half. Okay. We change colors for the 2s electrons. What's my value for N?
0.
If it's 2s, N, well, first off, N can never be 0. N,
Oh, well,
N,
I thought you were asking about L. My bad, I went ahead.
that's okay.
It's
Yeah.
2.
N is 2, L is 0. Yep, if L is 0, M sub L has to be 0. I've got 1 spin up and 1 spin down. All right. Changing colors once again. Let's do the 2 P's. N, L, M sub L, and M sub S. For all of these 2p electrons, what's our value for N?
2.
2. For all of these 2p electrons, what's our value for L?
1.
1. Okay. I'm going to go for just this first orbital first. What's that M sub L value?
-1.
-1, excellent. And in that orbital, we have one that's +0.5 and one that's -0.5. How about in that second orbital? What's our value for m sub L?
0.
0. We have only one that's spin up, so +0.5. And then this last orbital, what's our value for m sub L?
1.
One.
1, and we have a positive spin. If we double check, we see that no two electrons have the same 4 quantum numbers, right? Some of them are sitting real close together in our stadium, but none of them have exactly the same 4 quantum numbers. Okay. Another thing that we could do here is to say, you know, the draw on an orbital diagram like this, circle an electron and tell me those 4 quantum numbers, right? You know the shell, you know the subshell, you know the orbital, and you know whether it's spin up or spin down, right? And so we could ask this kind of question in lots of ways. Okay. All right. Before we go for today, I told you that I'd give you a little sneak peek, another tool to use instead of that diagonal arrows. We can use the periodic table. The periodic table is broken into these blocks, right? Here in brown, we have the S block. All those elements, their last electron is in the S subshell. Over here we have the P block for all those elements except helium. Notice that helium really belongs over here, right? Because he has an S. But for all of those elements, their last electron is going to be in the P block. Here in the middle, we have the D block. And down at the bottom, the F block. You cannot see that green, that yellow, I'm pretty sure. So let's make it the F block. Okay. And so if you just go across the periodic table, you can use this. We're going to do the 1s first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s. Now comes the 3d. And so for the S block and the P block, right, this is period 1, and we're in the 1s, right? Here we have period 2, and we're in the 2s. Here we have period 3, and we're in the 3s. The D blocks are all shifted down by 1. Right? Right? And so the 3Ds are actually in the period 4. The 4Ds are in period 5, right? That's just one thing you have to keep in mind. This periodic table doesn't show it very well, but these 2 blocks right here actually fit in right there to right there, right? And so let's just imagine that those really get snuck in there. And so by the time we're down here to period 6, before we come to the 5D, we're going to have the 4F, right? And so the F block is shifted down, shifted down 2 periods. Okay. So we have the S block. The S block is whatever period it's in. We have the P block. The P block is whatever period it's in. The D block, those transition metals in the middle, shifted down by 1. And those F block, we call those the inner transition metals, shifted down by 2. Okay. We're going to do some more practice with this on Monday. I hope that you have a fantastic weekend and enjoy the rest of your Friday.
You too. Thank you.
Thank
Thank
you.
Thank
So long.
you.
Thank you.
Thank you so much.